Okay, so this is your video for 11.1. We're beginning circles. Circles is very vocabulary intensive and very theorem driven. So we're kind of getting back to like chapter 2, chapter 4. So you're going to really need to stay on that vocabulary and theorem chart. Okay, so remember from your vocabulary chart that a chord is a segment that touches the two endpoints. So, or that whose endpoints touch the edges of a circle. So JM is a chord. KM is a chord. I think that's all we got there. Radii go from the center outside. So LK is a radius. LM, LJ. Or I could have named those JL, KL. They can be named either way. A secant is a line that goes all the way through a circle. So the line JM is a secant. Now that's kind of confusing to some people. The line segment JM is a chord. The line JM is a secant. So be careful with that. A diameter is a chord that goes through the center of the circle. So KM is a diameter. So every diameter should also be a chord, but not every chord will be a diameter, so be careful with that. A tangent is a line that goes through and just touches the circle. So line M, how about line M, not line M? Line M is a tangent, and point H would be the point of tangency. So you really have to know those vocabulary words because there are a lot of them in this chapter. Alright, find the length of each radius and identify the point of tangency and write an equation of the tangent line at this point. So, S, the radius for that circle, let's name this T, so just so we can have that easy. So ST is 2 units. No, it's not. It's 1.5. I'm on crack. RT is 2 units. The point of tangency, we would call that T. And T is located at -2, 0. And the line of tangency would be the line that cuts right through here. So that would be y is equal to 0 for your line of tangency there. Okay. Moving on. Oh no. Oopsie. Sorry, I used marker and it bled through. My bad. Alright, early in its flight to the Apollo 11 spacecraft orbited Earth at an altitude of 120 miles. What was the distance from the spacecraft to the Earth's horizon rounded to the nearest mile? Okay, so out here will be your spacecraft and it will be 120 miles. What is the distance from the spacecraft to the Earth's horizon? So that is really asking like this. The Earth's horizon would be where it's tangent to the Earth, so they're really asking for this distance right here. Okay, so a couple things you need to know for this. We need to know that we are going to draw in 2 radii in order to make this a triangle right here. So these are both radii, so they're going to be congruent. That theorem 11.1.1 in your book says, in your vocabulary chart, says if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So basically, anytime a radius and a tangent line run into each other, they're going to be perpendicular. So that tells us that this is a right triangle right here. Okay, and the other thing we need to know, I'm sure that y'all all know and you should have committed to memory, probably not, is that the Earth's radius is 4,000 miles long. Okay, so this is 4,000 and this is 4,000. So once you get this picture drawn, it's pretty easy to figure out that all you have to do is Pythagorean theorem, because you have a right triangle like this. This is 4,120 miles. This is 4,000 miles, and I just want to know how long that is right there. So let's do 4120 squared minus 4,000 squared. That is 974,400. So let's take the square root of that. It's a word problem, so that makes it easy for us. So we can use a decimal, so that would be 987.1, oh, rounded to the nearest mile. So 987 miles. Okay, so this will be difficult until you get the picture drawn. So, and I was just teasing about you knowing the 4,000. I would give you that information. But what you need to know is that you might have to draw in your own radii wherever it would be convenient for you to do so. And then you need to know that a radius and a tangent line are perpendicular so that you would know that that was a right angle. And then once you did that, that's the hard part. And then you would know that the math, that those, you could just do a simple Pythagorean theorem. Okay, the next one, example 4, comes from the next theorem in your vocabulary chart here. And it says if two segments are tangent to a circle at the same external point, then the segments are congruent. So basically, anytime you have this like ice cream looking shape here, where you have the circle and two tangents coming out, you can know that these two tangents are going to be congruent to one another. Okay, so that's what we have right here. Once you know that that's what you're looking at, this problem becomes very easy. And you can say, by theorem 11.1.3, I know that 4 plus 2a is equal to 5a minus 32. If you don't know that theorem, then this could be quite difficult. So then once we set that up, we could just solve using regular algebra. A is equal to 12. So we're going to plug that into HG. Oh my gosh, the hits just keep coming tonight. We got a crying baby and a whining dog. Alright, so that would be 28 for HG. You could also plug that into HK, and you should also get 28 because they better be congruent, otherwise you did the whole thing wrong. Okay, so this one doesn't tell you what it's after. I forgot to type that in there. It's asking you to find the measure of angle SQT. So this is the same setup as the last problem, only they were wanting to know side lengths. And now we're using the same setup, but we're going to talk about angle measures. So you kind of have to use the last two theorems together in one. So I'm going to draw in the radius from Q to S and the radius from Q to T. And I'm going to know by theorem 11.1.1 that these are going to be perpendicular. So they're going to be right angles right there. Okay, a little fact that you don't have to know to do this problem, but maybe you would for a future problem. Theorem 11.1.3 tells us that SR is congruent to TR. We also know by definition of a radius that SQ is congruent to QT because that's what a radius is. So we can tell that this shape is a kite because we have we know by definition of a kite, we have two consecutive pair of congruent sides. So this shape would be a kite. Now all we need to know about it is what we know about our interior angles. So I know, oh shoot, what's that stupid theorem called? So, I don't have to know it's a kite, but I do know it's a quadrilateral. So, by the polygon angle sum theorem from chapter 6, I know that any quadrilateral adds up to 360 degrees. So, I've already used 180 from the two 90s. So I'm down to 180, and I've already used the 22 from this right here. So this angle SQT, excuse me, must be 158 degrees. Okay, we're not going to do any formal proofs for chapter 11 for circles, but I am going to ask you to get back to justifying your steps that you have. So we used a lot here. 11:1:1 to tell that these are perpendicular. 11:1:3 to mark these as congruent. Definition of a radius to mark these congruent. So that let us know that this was a kite, which we didn't have to know, but it's nice too. Polygon angle sum theorem told us that this has to be 360 altogether, and then I just solved from there. So 158. All right, see you next time.